Kinetic energy. The work kinetic energy equation. When a constant external force acts on an object in the same direction of its displacement, positive work is done. We've shown this before, but we're going to do it again here. There's the force, there's a displacement, they're in the same direction. So we can use this equation for our work. We don't need the cosine theta here, because cosine of 0 degrees is 1. We're going to substitute in for force, ma, right? Newton's second law. Next, since we have a constant force here, we're going to take the third kinematics equation. And what are we going to use with that? We're going to solve this equation for AD. Now that seems a little funny, but just bear with us here. So we subtract V0 squared for both sides, so it moves over to the left. Then we divide everybody by 2. So we have AD is 1/2 V final squared minus 1/2 V0 squared. Here's the two equations from the previous slide. This was from the work equation, and this was from third kinematics. Look at this AD over here, which is equal to all of this. We're going to put that in right there. So we now have work is mass times 1/2 V final squared minus 1/2 V0 squared. And then we'll just write it like this. We'll distribute the m through the parentheses. The right-hand side of this equation represents the change in the energy of motion of an object, right? We've got the velocities there, and it's changing from an initial velocity to a final velocity. Each term now is defined as the kinetic energy. Perhaps you've seen that formula somewhere in your studies before this course, but this is where it comes from. So we're going to write kinetic energy is 1/2 mv squared. The equation is the work kinetic energy equation. Net positive work applied to a system increases its kinetic energy, and once again expressed in joules. Now this is a key point here. Later in the unit, the work kinetic energy equation will be expanded to include all different types of energy, not just kinetic energy. How does this work if we have a displacement in this direction and a force in this one? And the example we've used earlier is putting the brakes on a car. This time the work done by the force on the object is negative. So we now write our work kinetic energy equation like this. Minus W is equal to 1/2 mv final squared minus 1/2 mv0 squared. We replace each one of those guys with the kinetic energy, and we show that kinetic energy final is equal to the initial kinetic energy minus the work. And then we'll go back here, and what we're showing is that since negative work is done on the object, its kinetic energy and the velocity decrease. So Vf is less than V0, which once again, if we go back to the car example, when the brakes are applied, the car slows down. How much kinetic energy does an 80-kilogram man have while running at 1.5 meters per second? Here's our givens. We write the kinetic energy expression, substitute in our numbers, and we get 90 joules. A bird flies at a speed of 2.5 meters per second. If it has 14 joules of kinetic energy, what is its mass? Once again, we start with the kinetic energy equation, but we're looking for mass, so we want to rearrange that formula for m. Multiply both sides by 2, then divide through by v squared. Put in our values, and make sure to remember the 2 there, and we get a mass of 4.5 kilograms, which winds up to be about 10, 11, 12 pounds. It's a pretty heavy bird. A 400 kilogram car has 1.8 times 10 to the 5th joules of kinetic energy. How fast is it moving? Start with the givens and the kinetic energy equation. We need to solve this for velocity, so multiply through by 2, divide through by m, and then make sure you do this step. Velocity is the square root of 2 times the kinetic energy over mass. Put in our numbers. And again, make sure when you do this, the square root sign encloses all those numbers. And what we get is 30 meters per second, which is about 62 miles an hour.